Alright, so what we're going to be doing today, guys, is starting to take a look at these graphs of polynomial functions in a little bit more detail than what we did in the previous section. Because in the previous section, we figured out, okay, when x gets really, really big, here's what the graph is doing. When x gets really, really small, here's what the graph is doing. What we're going to be doing in this section is getting a little bit more detailed, and one of the things we're going to be looking at especially is something called maxes and mins, kind of the peaks and valleys of the graph. Okay, so this one, we're going to graph this function by making a table of values. Making a table of values, unfortunately, there's no one formula that I can give you, like, hey, these are the exact values that you should use. A really good way to start off is going from -2 to 2, and so we're going to set up a table like that, look at the graph, see if we need more detail, and then maybe revisit our table. Okay, so we're going to start with x and y. So a good place to start is from -2 to 2, and then like I said, we'll see if we need to fill in any more detail than that. So we are going to open up a calculator page, and while you're doing this, it'd be great if you could kind of follow along, and that way you know how to use your calculator to do these when you are doing them on your own. So we're going to plug into this equation right here all of these values. So we've got, like x to the 4th, we need to put -2 to the 4th, and then minus -2 to the 3rd, minus 2 times -2 squared, plus 4 times -2, and then minus 6. Okay, so we plug that in, and we get 2. Okay, so that's a good start. So we plug that in, we get 2. Then we're going to try -1. So let's just copy paste, and then everywhere there's a -2, we're just going to replace it with a -1. Might save a little time from plugging the whole thing in again. So change it to 1. 1, -1, -1. Okay, that gives us -10. Okay, and then 0 is super easy to plug in because this would be 0, 0, 0, 0, -6. Okay, let's try the 1. So let's go through, copy paste this, and this time I'm just going to get rid of all the negative signs. Delete that. Now we're plugging in +1 instead of -1. Okay, we get -4 for that. Okay, and then I'm going to replace all of them with a 2. Okay, so replace that one with a 2. Whoops, no. Shoot. Okay, let's try that again. So 2, and that should be squared. And that gets us to 2. So like I said, we're going to look at the graph, see how it looks, see if we need to fill any more details in. If we do, then we'll add more to our table. Okay, and then let's go in terms of 2. These are all even anyways. That should be nice and easy. So -2, -4, -6, -8, -10, and then 2, 4, 6. So first we've got the point -2, 2, so that's going to be right there. Then the point -1, -10, then 0, -6, 1, -4, and then 2, 2. Alright, so it looks like we could probably use a little bit more detail there. It's kind of hard to see exactly what's going on. But we could, you know what, we're going to give ourselves just a pretty good sketch from that, and it's not going to look great, but we're going to kind of follow exactly what this is telling us to do. Alright, so the graph is going to look something like this. It'll come down through this point, and then it'll kind of turn around here, maybe go like that, and then come up through that point. Okay, so something like that is a very general sketch that we have. And look at the way the graph bends. See here how the graph is kind of bending upward, then it's still bending upward. Then we hit that point, we're going to switch to it bending down and then bending up. You're kind of changing the shape of the graph as you go. And since we're doing just a very simple table, these aren't going to be the most perfect graphs. We're just looking for some very little details, like how low does the graph go and what does it look like at the two ends. Notice here on the two ends how we're going up to infinity, up to infinity. We could have figured that out from looking at the leading term. Since it has an even degree, we know both sides are going to do the same thing, and since there's a positive number in front, we know they're both going to go to positive infinity. All right, so we're going to talk about something called the location principle. The location principle is going to help us to find exactly where the x-intercepts are, or where the zeros are of this graph that we can draw. And so what the location principle tells us, and this is kind of an easy idea that we could see by looking at these graphs, the location principle says if the graph of the function changes signs, there is a 0 between those x values. So let's write that down. So if the value of f of x so the function value, the y value, if it changes signs from one value of x to the next, then there is a 0 between those two x values. Okay, so we'll look at that definition and then I'll kind of compare it to the graph that we're looking at here. So here I've got a positive value, then a negative value, which according to this principle means there must be an x-intercept or a 0 in between these two values, which in between -2 and -1, there is a 0 right there, an x-intercept, and it's right there. Then I'm still negative, still negative, still negative, then I switch to being positive. So the location principle tells me there must be a 0 in between these two values as well, somewhere between 1 and 2. So if I'm looking here, somewhere between 1 and 2, there's a 0. There's my x-intercepts. That's what my location principle tells me. So I'm going to use that idea right down here in the next example. So I'm going to do the same sort of thing with this. Just going to do my best to kind of come up with some of these values. So guess what I should have on the table and then see if I need to fill in any more details from there. And I'm going to use that to figure out where exactly my x-intercepts should be. Okay, so like I said, we are going to set up that pretty much that same table that we did before. All right, so okay, so we're going to do the same thing. Oops, I can't see that. There we go. We're going to do the same thing where we plug in some of these values right into the table, or I'm sorry, right into the calculator, and then we will get those x values. So add a new calculator page. So we're going to plug in -2 to the 4th, minus 3 times -2 to the 3rd, minus 2 times -2 squared, plus -2 plus 1. Okay, so that gives us 31. So it's going to be a little far off our graph. So that will probably not appear on there anywhere. Then the -1. So let's go in here, change every -2 to a -1. Okay, so that gives us 2. So we still don't have a 0 anywhere in here because these values are both positive. Then if we plug in a 0, we've got 0, 0, 0, 0, 1. So still no x-intercept in there. Then let's plug in 1. So here I'm just going to get rid of those negative signs. Okay, so this is plugging in +1, and I get a -2. So we're going to have a 0 somewhere in there because there's a sign change. And let's plug in 2. Okay, so that gives me a -13. Okay, so what I see on here is just one x-intercept. Let's see if we need to go any farther. All right, so let's maybe plug in a couple more values, maybe plug in a 3, plug in a 4 to see if we can plug anything else in. Because this is going up to 31, which means my values are just going to keep getting bigger and bigger. But my graph went down. It has yet to come back up. And we know that this is a positive x to the 4th, and so my graph in general is going to look something like this. It's got to go down, but then we know at the end it has to come back up. So let's try a couple more values here. Let's try plugging in a 3 and see what we get. Okay, so change all of these 2's to 3's. Okay, I get a negative 14. Okay, it's still got to come back up. So let's try the 4. So like I said before, there's no like perfect directions that I can give you for these. You just have to kind of play around until you get what you know the polynomial is supposed to look like. 37, there we go. That's more of what we're looking for. Okay, so it turned back around in there somewhere. So 37, so according to the location principle, remember it says if the value changes sign from one value of x to the next, so changes from either positive to negative or negative to positive, there must be a 0 somewhere between those two x values. So here, my values of f of x change from positive to negative, then later they change from negative to positive. So there must be a 0 in between there somewhere, because I'm above the x-axis, then I'm below, and here I'm below the x-axis, then I'm above. So it must happen somewhere in there. Okay, so let's say between 0 and 1, and then again between 3 and 4. Okay, and let's sketch a little graph. Okay, and we can go by 2's again. 2, 4, 6, 8, 10, 12, 14, 4, 6, 8, and we're definitely not going all the way up to 31. So this point will be way, way, way up here. Negative 1, I'm here at 2, 0, 1, remember that goes halfway, 1, negative 2, 2 is down here at negative 13, halfway between 12 and 14, then at negative 14, and then we jump way up here to 37. So again, way, 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 way high. So this starts way high up here, comes down, comes through this point, comes down here somewhere, and then it shoots way, way up. Because my graph is going to look something like that. But I see that I cross through the x-axis right about there, somewhere between 0 and 1, and then I cross through the axis right about there, somewhere between 3 and 4. Alright, so that's what we're looking for. Very, very general sketch of the graph. Okay, so now we're going to talk about something called relative maxes and relative mins. So let's look at those definitions. Okay, so minimum and maximum points. So again, we have these things called relative maxes and relative mins. So we say that a point is a relative max of the function since, let's say a point where no other nearby points have a greater y coordinate. And we say it's a relative max because it's a maximum relative to the points around it. Nothing in the general vicinity is higher. It doesn't mean there aren't other points at all that are higher. And then same thing for the relative min. We say that a point is a relative min since no other nearby points have a lesser y coordinate. So a point where no other nearby points have a lesser y coordinate. Okay, so get those definitions down. I'm going to make a really quick sketch so you guys can just see what I mean by this. Okay, so quick sketch. So say something looks like this. Kind of a nice little run-of-the-mill cubic graph here. We say that this one right here is a relative max, and that's because no other nearby points have a greater y coordinate. If you look around in the general vicinity, this is the highest y coordinate. Now granted there are higher y coordinates elsewhere, but in the general vicinity this is the highest one. And then we say this one is a relative min because none of the other nearby points have a lower graph. So relative max, relative min. Doesn't mean it's the biggest point ever or the smallest point ever, but just the points in the general vicinity are no higher or no lower. This is an important thing right here. So the graph of the polynomial n has at most n minus 1 turning points. So we call both of these, either maxes or mins, turning points, and that's literally where a graph turns around and starts going in the other direction. Alright? Example 3, we're going to graph this function right here. Estimate the x-coordinates at which the relative maxima and minima occur. This is like a Latin thing, maxima and minima. Those are the plural for maximum and minimum. Alright, so we're going to do a very quick sketch of this here, and we can do the table thing again, where we just kind of use a handful of table values to approximate. So let's get this set up. So we want to graph these functions, so we'll start with these values that we used before, the -2 to 2, and then we'll see if we need to add anything else in. So we're going to plug these in. We've got our calculator page here. Let me clear that off. So we're going to add some more values in. So we plug in -2, so we've got 2 times -2 cubed plus -2 squared minus 4 times -2 minus 2. Okay, so that gives us a -6. Then I can plug in -1. So I'm going to go up here, replace all of my -2's with -1's. Okay, that gives us 1. Then when I plug in 0, 0, 0, 0, -2. Okay, let's try 1. So now I'm going to go in here, delete all the negative signs, so I'm plugging in +1 instead of -1. Gives me -3. Then I can plug in 2. Again, replace all of the 1's with 2's. Oops, that one. Okay, and then I get 10. Okay, so let's give a quick sketch of the graph, see if there's anything else we need to add in here. Okay, so we're going to go up by 2's again. 4, 6, 8, 10. -2, 4, 6, 8, 10. So at -2, we're down here at -6. -1, we're at 1. 0, we're at -2. 1, we're at -3. And then 2, we're back up here at 10. Alright, so this graph is going to look something like this. It's going to go up somewhere probably a little bit past this point, come down probably somewhere down here, come back up here, hit this point, and then go straight at that high point right there. Okay, so that is my best sketch of the graph. Okay, so when we're talking about a relative min and a relative max, relative min is going to be somewhere around here, relative min is going to be somewhere down there. Okay, so when we're trying to approximate, we can figure out where the zeros are. We know that there are zeros somewhere in here, because this is a change from negative to positive, so I had one somewhere in there. Then this is another change from positive to negative, so there must have been one in there. Then I change again from negative to positive, so I must have had a third zero somewhere in there. So we've got these two turning points. We go up to a high point, down to a low point, and then we finish going up and up and up. We are going to just approximate where the value of the relative max and relative min are. We can say that it's near a certain value. We can say that it's in between a certain value. And so if we look, like this value right here is higher than all the other surrounding points. Okay, so it must be somewhere near x equals -1. So let's say relative max near x equals -1. So it's somewhere around that point. It's probably higher a little bit later. And then this is the lowest point that we have in the general vicinity, this -3. So we say there's a relative min near x equals 1. If we wanted to be really, really precise, we could say somewhere between -1 and 0, but it's actually closer to -1. And then we could say somewhere between 0 and 1, but it's actually, again, closer to 1. So this is totally fine to say what it's nearest to, and it's not going to be perfect. Okay, so this last one that we're looking at, nice little story problem, the annual sales of fax machines for home use, because that's relevant now. We've got this nice polynomial, 4th degree, very beautiful coefficients, where x is the number of years after 1990. Okay, so good. Hopefully it'll show that fax machines are slightly irrelevant now. f of x is the annual sales in millions of dollars. So we want to start by graphing the function. We are going to graph the function in our calculators. So I want to show you how to do that. We're going to play around with the window a little bit. So open up a new graph page. We're going to graph this function exactly the way we see it here. So negative 0.17 x to the fourth plus 6.29 x to the third minus 77.65 x squared plus 251 x plus 1100. Okay, so we really see a very, very limited amount on the graph here. So let's start with our window. So press the menu key, then we've got this nice window zoom key that we're going to go with, and we're going to do window settings because we're going to change the windows on our own. So, x-min, remember it says right here, x is the number of years after 1990. Okay, so we could still tell time before 1990, so I guess negative 10 would be good, because negative 10 would go back to 1980. Now, if we go down here, it's the x max, it's only 2014, just about 2015, so the most we can go is 25 years after that, because then we'd be going into the future. So hit tab a couple times. And then we are talking about the sales in millions of dollars. So it probably won't be anything negative. They're not losing money. Just in case, let's put like a negative 10 there or something. And then I don't know how much they expect to sell in millions. Let's try like 200 and see if that hits anything. So go ahead, hit OK. We'll see if our graph shows up. Okay, so it does go way, way higher than that. All right, so the only thing we're going to have to see is this graph goes up. We can't see it. And then it must come back down. So the only thing we're going to change is how big that goes. So let's hit menu again, window zoom, window settings. Let's leave the x values the way they are because that's just fine. Let's maybe go down to negative 100 just to see if there's anything down there. Hit y max, let's go 500. Okay, still not a great picture. All right, so let's see if we can go even higher than that. So now the only thing we want to change is that y max. Let's try 1,000. Hopefully this is our last one. No, still not our last one because we can't see where that high point is. So let's, one more time, let's try 1,500. Please work. There we go. Now we can see that high point right there. And so that is when fax machine sales were at their maximum, and then as you can see, they are clearly declining after that. So part A, graph the function. Part B, describe the turning points of the graph and its end behavior. Okay, so the turning points, we've got this point right about here, and that's where the sales were at a maximum. Okay, so the turning points, let's say we have a relative max, near, and then if we look back at this graph, this high point right here traces down to about 1, 2, 3, yeah, maybe 3. Relative max near x equals 3, which if that's the years after 1990, that would be the year 1993. Which makes sense, you know, before you were born, that's when fax machines were at their peak. And describe the end behavior. Both of the end behavior goes down towards negative infinity. So end behavior, as x approaches negative infinity, the graph approaches negative infinity, meaning it goes off to infinity towards the left. And as x approaches positive infinity, meaning as we look to the right in our graph, the function is again headed down towards negative infinity, which should make sense because I have an x to the fourth, which means the end behavior matches, but I have a negative in front, which means they're both going down. What trends in fax machine sales does the graph suggest? Well, the graph suggests that fax machines are not so popular anymore. Say fax machine sales are quickly declining. Okay, and is it reasonable that the trend will continue indefinitely? Well, no, they're not just going to keep losing and losing and losing money. Eventually, they'll probably get rational and stop producing them. Because it looks like right now they're losing money and they're not going to keep doing that. Eventually, they'll give up and just stop selling the darn fax machines. All right, so that's it.